All righty. So we said we were going to take a look at some of these practice problems from the textbook. So the first one, just to get a little practice on nomenclature. It's always good to work on nomenclature because it's always something that comes up in quizzes is how to name a compound. Now, you can see that the longest chain in this compound has 6 carbons. It doesn't matter if we start at this carbon that I have in the red circle or if I start at this carbon in the blue circle. Either way, it's some kind of 3-hexene. 3-hexene. But my question to you is, should I start numbering at the red circle or at the blue circle? And it's not a trick question. It's just based on, knowing what the tiebreaker would be here, because it's not the triple bond. Yeah, I started numbering at the red carbon. Thanks, Sean. Yeah, absolutely, because then I've got 2,2,5 trimethyl as opposed to 2,5,5, right? So there we go. So we're going to start numbering at the red carbon. So I'm just going to put here 1, 2, 3, 4, 5, 6. So we've got 2,2,5, 2,2,5 trimethyl 3-hexene. Okay, it says a systematic name. It doesn't mention common names, but you could give it a common name as well. So common, I'll put it in red. Right here I have an isopropyl group, and here I have a tert-butyl group. So you could call it tert-butyl isopropyl acetylene. Anyhow, you could call it that if you wanted to. The next one, same question. If I put a green circle here and a black circle down here, where should I start numbering? Could anybody tell me? And it's not meant to fool you or anything. It's just a genuine question. What do I want to do? I want to give, yes, the green circle, right? I want to give the triple bond the lowest number possible. Exactly. So I'll put the numbers here in red. So we're going to have 1, 2, 3, 4, 5, 6. So this is a 2-hexene, and we've got 4,4-dichloro. So we'll scribble this down. This is 4,4-dichloro. 2-hexene. Great. The next one, I'm pretty sure you could name that one in your sleep. That's 1-hexene. So 1-hexene. And if you called it hex 1-ine, that's also acceptable, right? That's fine. You could also give this a common name. You could call it butyl acetylene. I don't know who would do that. That's kind of weird to call it that, butyl acetylene. But I guess technically it's correct. And the last one, you can clearly see that you should start numbering down here. 1, 2, 3, 4. So we've got a 3-bromo, 3-methyl. So this would be a 3-bromo, 3-methyl, 1-butene. Yeah. And there you have it. So a little bit of practice on nomenclature. All right. Usually students are very good at alkyne nomenclature, but if you have any questions, don't hesitate to fire away, and I'd be more than happy to talk about them. All right, question 9.35 says draw the products of each of the following acid-base reactions and then predict the position of the equilibrium. So if we start out with the mechanism here, it doesn't ask us to do that, but we're going to do a deprotonation here. And that's going to give us, I'll just draw an arrow this way, that's going to give us an acetylide plus butane is what you would get. Well, the pKa of an alkane is around 50, and the pKa of an alkyne is around 25, so we'll put 25 here. And remember, the equilibrium is going to lie to the side of the stronger acid or weaker acid. Which side will the equilibrium lie to, the weaker acid or the stronger acid? Could anybody answer that? Weaker or stronger? Yes, exactly. It's going to lie to the side of the weaker acid. So our equilibrium is going to look something like this, right? Where it's mostly going to be the product here. In fact, it would basically give you only the product in this case. You could even eliminate this error. I mean, the difference in log unit, we're talking about 10 to the power of 25 here. That's a pretty big difference. All right, the next one, we're taking a terminal alkyne and we're deprotonating with sodium hydride. I'm just going to draw the hydride ion here and draw the deprotonation like this. So this gives us this alkanide plus hydrogen gas. Now the pKa of hydrogen gas, it's something that we don't talk about a ton, but it has a pKa of around 38. you know, 38, something like that. And the pKa here is going to be 25, of course. And so you can see that the equilibrium is going to lie to the side of the products because hydrogen is a much weaker acid than the terminal alkyne is, so something like that. All right, there we go. So yes, sodium hydride and butyllithium, both of them are good enough bases as a deprotonated terminal alkyne, and you can also use sodium hydride. In fact, that's the one we've used the most in our practice problems. So let's get some practice on just going through the reactions and, you know, finding the conditions to do each one of these reactions. Why don't we start with this one here? If I want to take an alkene and convert it all the way, or sorry, an alkyne and convert it to an alkane, could anybody help me out with the conditions on this one? So for this one, it's just going to be a straight ahead hydrogenation, right? Just hydrogenation using hydrogen gas and palladium, platinum, or nickel. All right, so that's just a straight ahead hydrogenation. We're going all the way from the alkyne to the alkane. The next one, so we're going to go let's go clockwise. Let's go clockwise. So next one we're going to do is this one. This one is a Markovnikov addition of HCl, but we only have one molecule of HCl being added, so we'll just put HCl like this. If you go to the this one here, okay, where you have the geminal dibromide, well, in that case, you're using HBr, but it's going to be excess HBr, right? So you need more than one equivalent. So we'll put excess HBr, and over here we'll write one equivalent. All right. The next one, we're going from a terminal alkyne to a terminal alkene. This is something that I haven't covered with you yet, but the only way you can do this is by using hydrogen gas in Lindlar's catalyst. So I'll write here, terminal alkyne reduction will not work with sodium metal reduction. Okay, so sodium metal reduction doesn't work for a terminal alkyne. It has to be hydrogenation conditions. All right, the next one is an ozonolysis reaction. So we want to clip the molecule here. And so for that, we're going to use ozone in the first step. Does anybody remember what the reagent is in the second step? Yeah, thanks a lot. It's going to be just plain old water, exactly. And since we have a terminal alkyne, we also get carbon dioxide in this one. The next one is the Markovnikov addition of water. So this one is Markovnikov addition to give us a methyl ketone. So for that, we need aqueous acid. So we need sulfuric acid and water. But remember, to get that reaction to work, you have to have mercury 2 sulfate. And there, the next one is an anti-Markovnikov. So this is anti-Markovnikov. So in order to do that, we're going to do hydroboration oxidation. So first step is going to be 9-BBN, followed by H2O2 and sodium hydroxide. And there we have it. So these are all reactions that it's crucial that you memorize each one of these reagents so that you're able to recall them, right? That's one of the difficult things about organic chemistry is the quantity of reactions you have to know. And then, of course, your ability to memorize them and recall them at a later time. So let's get some more practice on them then. And let's take a look at question 9.41, which states, predict the final products for each of the following reaction sequence of reactions. So for the first one, we're going to treat this molecule with excess sodium amide. So that's going to do a double elimination, right? There's 3 protons here. You do one for an E2, the second one for an E2, and the third one gets deprotonated to produce an acetylide. So what you, or sorry, an alkanide. So what you would end up with after the first step is this intermediate. You would end up with this here after step 1. So in step 2, we're treating it with ethyl chloride. So we have ethyl chloride, which looks like this, okay? And that's just going to do an SN2 reaction, so nucleophilic attack, loss of leaving group. And that is going to give us this product. So we have our triple bond, and then we have an ethyl group coming off. And then in the next step, we're treating it with hydrogen gas and Lindlar's catalyst. So H2, I can't see very well. Lindlar's catalyst. And could anybody tell me, if I'm using Lindlar's catalyst, will I get the cis-alkene or the trans-alkene? And it's not a trick question or anything. But I get the cis-alkene. Thank you. It's the cis, exactly. So there you go. So you end up with the cis-alkene. It's a beautiful thing. There we go. So there's our first sequence. The next one, we're starting out with acetylene. Remember, the simplest possible alkyne you can have is acetylene. Right? You've got to know the structure of acetylene, right? Just 2 carbons with a triple bond. So the molecular formula is C2H2. Okay, in the first step, we're going to treat it with sodium amide. So that's going to, I'm going to draw every intermediate. So that's going to give us this acetylide. Then in step 2, we're going to treat it with methyl iodide, like this. So that's going to do an SN2 reaction like this. And that's going to give us this compound, propyne. Then in the next step, next 2 steps, sorry, we're doing the hydroboration oxidation. So is this a Markovnikov or anti-Markovnikov? Exactly, it's anti-Markovnikov, isn't it? Yep. So we're going to draw the enol that we would get, which is going to look something like this. So this is our enol, but then it's going to undergo tautomerization. And when it undergoes tautomerization, it's going to give us this 3-carbon aldehyde called propionaldehyde. So base catalyzed tautomerization. All right, there you go. The next one is in a similar vein. The first 2 steps, no, actually they're not identical, are they? So I'll just do the first 2 steps kind of in one here because I think we've got this one down. We do a deprotonation followed by a treatment with ethyl iodide. And then in the next step, we're going to treat this with mercuric sulfate, sulfuric acid, and water. So I'll just scribble all those down here. So this is going to be a Markovnikov addition. The rich are getting richer. And so we're going to produce this enol. So let me just draw the enol, which is going to look something like this. Okay. And that, of course, is an enol. And the enol is going to undergo tautomerization. So this is the tautomerization process in acid. And it's going to give us a methyl ketone. So it gives us this compound, butanone. There we go. All right. Give me a thumbs up if you follow me on the last 2, the Markovnikov and the anti-Markovnikov. Everybody with me on those? Any questions about those? Okay, and again, don't hesitate to stop me if you have a question. The next one, we did something like this earlier today. We actually tried to make this same alkyne, this same ketone earlier on today in a previous video. You would have seen that, and we said, well, it should come from this terminal symmetrical, this internal symmetrical alkyne. That's what it should come from, right? And we went over the reasons for that because it doesn't matter which side you put the hydroxyl on, right? If you put it in the carbon in blue, you end up getting this compound. So the compound that's written in the red circle, right? But if you put it on the carbon in green, I don't know if you can see the green ink here, but you end up with this, right? And these 2 things are identical. So it wouldn't matter which one you put it on. And so you can see that all we need to do is add an ethyl group to one side, right? We just need to put an ethyl group. And so could anybody tell me what the first step is going to be, is to treat it with which base? What base would I use here to deprotonate? I could use sodium amide. That would work, right? So sodium amide in the first step, and then I could treat that with ethyl iodide in the second step, and that's going to give me the alkyne that I want. And then to get from here to here, I just need to do a Markovnikov addition. So I'm going to treat it with sulfuric acid and water and mercuric sulfate. All right, good. The next one, we want to take a dihalide. So let me just put a line here and a line here. We want to take a dihalide and we want to convert it into an alkene. Well, we know how to go directly to an alkyne, right? We know that if we take this geminal dihalide and we treat it with excess sodium amide, followed by H2O, that is going to give us a terminal alkyne like this. And then we said a couple of questions ago that if you want to go from the alkyne that is terminal to a terminal alkene, the only way to do that is using hydrogen gas and Lindlar's catalyst. Okay, the next one is something similar, isn't it? Because we want to add a carbon, right? We're starting out with 4 carbons and we want to end up with 5 carbons. Well, you can see that if we replicate the first 2 steps, so I'll just copy and paste this down here. So copy, and I'm just going to paste the exact same conditions down here. Okay, like this. Then we can add that methyl group on there, can't we? Right, by treating it with sodium amide, and then methyl iodide, and that's going to give us this compound, right? And then to reduce it to the transalkene, we're going to use sodium metal reduction. So sodium in liquid ammonia. That's what we would use to do that. Let's see here, because we were making a transalkene, so that's the only way to do that. All right, the next one, we're making a ketone. So for this one, again, the first 2 steps are the same as we saw before. If we take a geminal halide and we treat it with excess sodium amide and water, we're going to get the terminal alkyne, but now we're doing a Markovnikov addition, right? This is a Markovnikov addition of water across the triple bond. So we're going to use, you know what, maybe I'll do it this way. I'll write it out like this. I'll say we're going to treat this with sulfuric acid, water, and mercury 2 sulfate, and that's going to produce this enol, which is unstable. And the enol is going to undergo tautomerization to give us the methyl ketone. And of course, you need to know the mechanism of that reaction. So we could just kind of do an abridged, not an abridged version, but we could just kind of pencil the mechanism of tautomerization in over here. So we're going to have a proton transfer, which is going to give us this compound. Let's see here. Yeah, so we end up with a proton transfer. So we end up with this carbocation, which looks like this. And of course, this is in resonance with this oxonium. So let me draw the oxonium, which looks like this. There we go. And in the last step, the last proton transfer, is where water comes in as a base. And it's going to rip off the oxonium proton to give us the final product. So there you go. That's a mechanism that you have to be able to draw, acid catalyzed tautomerization. All right, the next one, again, similar vein. We're going to have to go through an alkyne because we know that if we have 1-butyne, we could treat this with 1 equivalent of bromine and end up with the trans-alkene like this, the trans-dibromoalkene. And so the first 2 steps are going to be the same that we kept using to make the 1-butyne. And then in the last step, we're going to treat this with 1 equivalent of bromine. Be very careful to add only 1 equivalent of bromine. All right, next one. Again, first steps are going to be identical. We're going to pass through 1-butyne again. So we pass through 1-butyne, and we know that if we want to make this secondary alcohol, we can just go through the alkene and just do a Markovnikov addition, right? There's nothing really new there. So the question is, well, how do we make the alkene? And we've looked at that already too, that you need to use hydrogen gas and Lindlar's catalyst to do that. So that gives you 1-butene. And then we just do a Markovnikov addition of water, no carbocation rearrangements to worry about. So we get that one knocked out. And that brings us to the next problem, which says, you know, how would you synthesize these molecules? So if I'm taking an alkene and I want to make an alkyne, well, the only way that we know how to make an alkyne with no change in the carbon skeleton, because here I have 6 carbons and here I have 6 carbons, this has got to come from a geminal dihalide. So let me write it out like we could do HBr, okay? And we know that if we do excess sodium amide followed by treatment with water, we could get the alkyne. So how do I make the geminal dihalide? Well, that's just a Markovnikov addition of sorry, I'm getting mixed up. I had it right the first time and I scribbled it off. Okay, so we need to make this dibromide, okay? The vicinal dibromide, which of course we can make, right, by taking this and treating it with bromine, and that's going to give us the vicinal dihalide, like this, okay? And then we can take that and treat it with excess sodium amide, followed by treatment with water, and that will give us the final product. All right, next one. It's in a similar vein to one that we looked at just a few minutes ago. We want to take a terminal alkyne and make an alkene. Well, you can see that we're going from 4 carbons to a total of 6 carbons. So that means I need to add these 2 carbons on the end over here. So for that, we're going to treat it with sodium amide as our base to deprotonate. And in step 2, we're going to treat it with ethyl iodide. And that is going to give us 3-hexyne. And then we want to reduce that to 3-hexene, trans 3-hexene. So we're going to use sodium metal reduction. So a little review of sodium metal reduction. And the last one is an exercise in adding more carbons. So we're starting out with a compound that has a total of 8 carbons. And then we have 6, 7, 8, 9, 10, 11. So we're adding 3 carbons. We're adding 3 carbons on the end here. And so for that, all we have to do is deprotonate and add propyl iodide as an electrophile. And so in the first step, we're going to treat this with sodium amide. And then in step 2, we're going to treat it with propyl iodide, and that will give us the propyl group, the 3 carbons that we need. So 1, 2, 3. And then to reduce all the way down to the alkane, we're just going to use hydrogen and palladium, platinum, or nickel. I'll put palladium. And there we have it. We've muscled our way through all of them. Steve? Yes.